entire unit talking about astrophysics. They've now folded it into other units. And that unfortunately brings us to a weird place where I have to teach you something, but the unit in which I should have taught it no longer contains the content. It's just been tacked around other various pieces of content. Which normally that would mean, well, I'll just, teach it my own way anyways. But this is the first year of the new content, so I am trying to be careful. We talked about orbits already a little bit. And I want to bring up a system. I'm going to try and draw it as carefully as I can, but in doing so, I will make mistakes, so there. So I want you to imagine the Earth, Moon, and Sun system. In this system, the Earth's orbit is very circular, but not perfectly circular. But we're going to treat it like it's a perfectly circular orbit. And we're also going to treat the Moon's orbit around the Earth as having a perfectly circular orbit. All right? So for the time being, just consider that the Earth is going this way and the Moon is going this way. It's kind of a complex dance. So far this year, we have, when dealing with gravity, we've generally considered, let me do it, just the gravity near the surface of the Earth, and talked about the fact that this mg is the weight of an object. In fact, from there we developed the whole idea that if you lifted an object a distance h above the ground, the whole screen is filled with blue? Well, you'll understand my dismay, because mine is not. Well, you can see this, so it's okay, but you get what I'm drawing. We developed, by talking about work, that the work done in lifting an object would give us minus mg h minus h naught as the amount of work done in lifting an object, and we defined that as the change in gravitational potential energy, because that would be minus the work done. These are all the definitions that we derived for potential energy, work, and applied it to gravity near the surface of the Earth. That worked great, and it gave us a clear understanding of how you could acquire something like kinetic energy by lifting something up high and just releasing it. Does that sound like something we've done in here? Well, what if we wish to go from the Earth to the Moon and wanted to calculate how much energy it would take to do so? Now, the reason you might want to do that, and I hope that you are smart enough to see why you might want to do that, if you want to figure out how much energy it would take, that would tell you how much fuel you would need, right? Otherwise, how do you know how much fuel you need? That's one of the things that I think you guys tend to not really appreciate, and I didn't appreciate for a long time. Well, I just figure out how much force it would take to get there and how long I would have to burn my engines for. That doesn't really work when you're trying to get how much fuel, because the amount of force you need changes as the mass of your spaceship is changing. You follow what I'm saying? So as you burn fuel, you can burn less and less fuel because your spaceship is becoming less and less massive. But also, we know that the force on the spaceship also will depend on how far away from the Earth we are, right? This changes. So although when you're near the surface of the Earth, that force doesn't change much, as you get farther and farther away from the Earth, it changes a lot. Of course, as you get closer and closer to the Moon, suddenly the Moon is pulling on you more than the Earth, and now you have a different problem, right? One of the things that we developed early on in conversations about this was needing a more practical approach for dealing with gravitational potential energy around a massive body when you're dealing with astronomy, right? Astronomical sizes. And what we've decided to do is consider the whole point of the reference place or the reference frame. Remember, when we dealt with gravitational potential energy, one of the things we always talked about was providing reference, right? What are we going to use as our reference level when calculating gravitational potential energy? Do you guys remember that conversation? Well, suddenly the reference level means diddly here, doesn't it? Because the reference level with respect to the Earth can't apply to the reference level with respect to the moon. Right? Two completely separate reference levels. If I want to go from the Earth to the moon, I would probably need to figure out what's a good point of reference between the Earth and the moon, something I can count on. Now, some people would say, well, the sun. The sun would be a good point of reference. The problem is the sun has its own gravity. So if I use the sun as my point of reference, I still have the problem, but now I'm dealing with the fact that, okay, I've escaped the Earth, but maybe now I'm just falling into the sun because I didn't take into account the fact that the sun is also acting on me. So the truth is, we don't take any of these as our point of reference. Instead, our point of reference relies on finding a place in the universe where the force on us due to gravity is zero. So what we've done instead is defined gravitational potential energy as the amount of energy relative to a point infinitely far away. It sounds really, really weird. You just got to buy into it. But we're going to say, and I'll define it again, as the point of reference is a point infinitely far away. Now this has a couple of consequences. The first consequence is it makes all of our gravitational potential energies negative. And you're going to say, why? Well, that's a mathy question, and just trust me for a minute, I will explain. But it makes all of our gravitational potential energies negative. And our gravitational potential energy isn't particularly complicated. It's going to look a lot like the force due to gravity, where R represents the separation distance between the two masses. So if this is you on the Earth, well, that's how you calculate your energy relative to the Earth, your gravitational potential energy relative to a point infinitely far away when you're on the surface of the Earth. Now, part of the reason we use this method is because this means that that point that is infinitely far away is common to the Earth and moon and sun. There's a point infinitely far away that's common to all of those. And the reason it's negative is I want you to imagine what this actually means. It's negative because the Earth is a gravity well, meaning you fall into the Earth because it has gravity. It's attracting everything towards it. This represents the amount of energy that I would have to apply to myself to escape the Earth. If I wanted to escape the gravity of the Earth, I could add this much energy and bring my total energy to zero. And that would have me escaping the Earth. I would be able to get infinitely far away with a velocity of zero by the time I made it there. So imagine, if I wanted to leave the Earth, one way to do so is to add kinetic energy to make my velocities, to make my total energy zero. Okay. So I know right now that if I'm on the Earth, I am in a gravity well, which gives me negative potential energy. So I am going to use something that will give me a lot of velocity to escape that and bring my energy to zero. So I'm going to use this energy in the form of kinetic, like maybe right on top of a rocket or something that would give me a lot of velocity so I could escape the Earth. Now, I want you to imagine what this would tell me. If I work this out just a little bit, like maybe move this to the other side, I'm going to get 1/2 mass of me, v squared, equals minus mass of Earth minus mass of me, g over the radius of the Earth. It would be positive. I can cancel out the mass of me. I can multiply by 2. I can even take the square root. Why not? Now, what does this represent? It represents the escape velocity, right? This is the velocity I have to give any object on the Earth for it to escape the Earth's gravity. That's what this represents. This is how we frame potential energy for astronomical units. We do so by setting our gravity as a negative value and use a reference frame that's at infinity. If I give any object on the Earth this velocity, it will have enough velocity to escape Earth's gravity. Now, I'm being very careful here. What did I not include in that? It's in the picture. Yes, I can escape Earth's gravity just to fall into the sun. This would not allow me to escape the sun's gravity. This is not an escape velocity for the sun. But if I wanted to get away from the Earth and say go to Mars, this would represent the escape velocity to escape the Earth, and I could probably use it to get to Mars. Now don't get me wrong, if you fire something at this speed, it will not escape the Earth. This does not include things like air resistance and the friction due to the atmosphere. If you fire something at this speed, it will have incredible amounts of air resistance and will not escape the Earth. It will burn up and be destroyed. You have to actually slowly give things this velocity over many, many minutes to get it outside of the atmosphere and then continue to accelerate it outside of the atmosphere. If you don't give something enough energy, though, it just doesn't escape the Earth. It either falls back into the Earth or falls into an orbit around the Earth. So, I'll say it again. You don't have to understand why or the math that gets this. I will tell you where the math comes from. But you don't have to understand it to understand that the gravitational potential energy relative to any astronomical body is a negative value because we are trapped in a well.